One more example. I've written out the example for you. The region is bounded by y equals sine x for x between 0 pi, x equals 0, x equals pi, y equals 1. The axis of rotation is y equals 1. So here's the y-axis, here's the x-axis, and let me turn that around. Okay, so here's pi, here's 0, and I'm going to plot y equals sine x, which looks like this. Remember, the maximum value of y equal to sine x is 1. This is x equal to 0, x equal to pi, y equal to 1, and y equal to 1 of course grazes this at the top because the maximum value is 1. And the axis of rotation is also y equal to 1. So let me first outline the region that we're trying to rotate. This is going to be important in just a second. So that sort of heavily outlined region, everything in here, I have to rotate around y equal to 1. And that's the volume of rotation. So we take, as before, the variable s along the axis of rotation for a fixed value of s. Take the cross section, and now we have to pick a point on the circumference of that disk to define r, and this is where most people make a mistake. So the temptation is to pick this point, but this is not the right point to pick. What you want to do is pick the point where the disk intersects the original region that we rotated, and the original region is this guy. So you have to pick this as r, and so that's the rectangle that defines the coordinates in the rotational axis. So this has coordinates s comma r. If it has coordinates x, y in the original coordinate system, then that rectangle, the black rectangle, is this. This is x and this is y. And note that in contrast to the examples we did in the past, neither the red rectangle nor the black rectangle are contained in the other. And this is what happens when the axis of rotation, when you kind of rotate your volume above what the original region is. Okay, so let's write down the relations. X is the same, S is the same as X, Y plus R equals 1, so R equals 1 minus Y, and this point lies on this curve, so Y equals sine X. Since S is the same as X, and X for this problem goes from 0 to pi, the limits of integration are 0 and pi. Therefore, the volume that we want to calculate is 0 to pi r squared ds. So let's figure out how r is a function of s. R is 1 minus y, so it's 1 minus sine x, because y is sine x. X is the same as s, so this is 1 minus sine s. So the volume is 0 to pi, and I'll pull the pi out, 1 minus sine s squared ds. And now you just have to do the integral. So let me expand that. 0 to pi, 1 minus 2 sine s plus sine squared s ds. And so that's the same. The first two integrals are easy to do. The integral of 1 is just s. The integral of sine s is minus cosine x. So the minus cancels with that, and I get plus 2 cosine s. And all of this in the limit 0 to pi, and then the third integral 0 to pi sine squared s ds. And the last integral, the sine squared s, is students often find this difficult to do. So I'm going to show you the standard trick to do this integral. And the standard trick is to begin with the double angle formula for cosine. So cosine 2s equals cosine squared s minus sine squared s. And cosine squared s itself is 1 minus sine squared s. So you get 1 minus 2 sine squared s. And now we just rearrange. We take the sine squared s term on this side, the cosine term on the other side. So 2 sine squared s equals 1 minus cosine 2s, or sine squared s equals half minus half cosine 2s. So now remember, what we have to do is integrate sine squared s. So integral 0 to pi sine squared s, which is the same as half minus half cosine 2s ds. And this equals, so the integral of half is s over 2 minus half the integral of cosine 2s. The integral of cosine 2s is half of sine 2s, and all of this evaluated from 0 to pi. So this is fairly straightforward to do. So you do this, you get a number, and you do this, you evaluate this between 0 and pi, you get a number, you add up both of these numbers, and that's your answer.